Hello, everyone. Today we will talk about, I think, the most complicated topic of the course is zero-knowledge proof. But I will try to explain it by simple words, so for you to understand the whole idea, how it works. And of course, we will talk about more technical details. So let's start. First, start with the definition. What are zero-knowledge proofs? Actually, it is a way of proving the validity of a statement without revealing the statement itself. It means that we have two parts: the prover, the party which is trying to prove something, and a verifier, which is the verifier responsible for validating the claim. So zero-knowledge protocol is actually a method by which one party, the prover, can prove to another party, the verifier, that something is true or not true, without revealing any information apart from the fact that this specific statement is true. So strictly speaking, zero-knowledge proof doesn't mean that you will know nothing. It means that you will get an answer to a certain question in the format of yes or no, true or false. Let me give you an example. Let's imagine that we have a shop selling alcohol, and of course we want to sell only to those, depending on the country, who are 21 years old or more. Without zero-knowledge proof, if we are suspicious about the particular person buying an alcohol, we just ask to show your ID, and looking at the birth date, we understand that yes, this person is 21 years old or older, or no. What zero-knowledge proof lets us do? Zero-knowledge lets you as a customer, a buyer who are buying alcohol, you are the prover. You want to prove that you are 21 years old or more. You actually provide zero-knowledge proof, and the verifier checks this zero-knowledge proof, and the only answer from the zero-knowledge proof verifier, so the seller of the alcohol, gets is that if you are older than 21 years old or not. So yes or no, true or false. And the verifier by no means will know, is not able to understand the specific your birth date. So he or she doesn't know where you are. So they don't know your surname, your name, your birth date. They only get this proof that you're 21 years old, and that's it. So that's the whole idea around zero-knowledge proof. Of course, we can build much more complicated stuff, but let's go deeper into this. So this is all based on mathematics. So we mathematically demonstrate to the verifier that we've done some computation honestly, without revealing the details not requiring recomputation. So it's essential for Web3. Why it's essential for Web3? Actually, zero-knowledge proofs are giving us two very important things when we use blockchain. It's the privacy and the scalability. Let me give you an example about the privacy. Let's imagine we're building lending protocol, and we have a specific pool for only KYC addresses or persons, and we want this pool to accept to be supplied by assets only from those who have KYC. Because it's a public blockchain, it's Ethereum, for example, everyone sees everything. Of course, we do not want to show a specific ID. We do not want anyone on chain to know our name. But we can, if you have an issuer, which everyone is trusting, this issuer issues to us a specific claim, and we are, as a prover, based on this claim. For example, Binance can help give us a specific claim, and we can use this claim and generate the proof that we are KYC'd by Binance, for example, or by any other centralized exchange. Having this proof, we can put it into the Ethereum transaction and prove for the specific decentralized lending protocol that yes, we have KYC. Yes, I mean, that's true. True or not true? True or false? That we have this KYC, doesn't matter. It's from Binance. Actually, the protocol doesn't know our ID, what our citizenship, what's our name. The only answer from this proof is that yes, we have KYC. So that's privacy. And then looking at this specific transaction, it's not possible to understand any data except maybe for yes or no. But even further, we can go further. We can, and we will talk about it later, we can issue the proof that can only be used by a specific smart contract or address. So it means that this specific smart contract can understand and get this answer yes or no, true or false, but any other smart contract, anyone else will not get any idea from what we're exchanging. And of course, scalability. What's great about zero-knowledge technology is that it's a symmetry of computational costs and power we need to generate the proof and to verify the proof. What I'm talking about? I'm talking about that in zero-knowledge, it's quite we need quite extensive computational power to generate the proof, and therefore we can generate it off-chain. But when we the verifier can verify this proof in a very let's say with the minimum computational power, it means that even smart contract which is on chain can check our proof with very little gas costs and the cost of the transaction. That's also very important. That speaks for scalability. Okay, let's move on. More ideas about how classical proofs are working. So if we have our general system as it works now, we have some government ID agency, it's the issuer. We have some ID, maybe passport, maybe something else, maybe driver license, and it is called claim. If we speak about zero-knowledge technology, we have us, we are the provers, and we have someone who wants to verify our ID. So, for example, that's police on the road. We're driving the car. Police stops us. Says, can you show your driver license? We give a driver license, and this driver license, we have lots of information which is not needed by the police officer. Your name, your surname, when this number of this ID, when it was issued, I don't know, maybe something else. But actually, the only thing policeman should know about you that yes, you have driver license for this specific car, for this specific category of cars, and that's it. But more than that, the policeman has access to the centralized database where every driver license is stored. So this actually policeman may check if your ID is not faked, if it's valid. So he or she goes to this computer, checks your ID, and then confirms, yes, okay, move on. So the same stuff is with the tax office, and you name it, IDs, and all this excess of information which we bring with this ID to those counterparties who wants to check something about us. So it's, first of all, we have lots of information. We give this information, which is excessive, to those who check us. These people actually can exchange information without our permission with the issuer, because we do not permit this check. And this is how it works now. What zero-knowledge proofs are changing in this order, in this architecture? First of all, we, in the same way, receive so-called claim or ID from the government agency, and that's it. That's it. Nothing additional is required. It means that having this claim, we can prove anything we want to the policeman, to the tax office, even to the smart contract, which is also verifier, sits on the blockchain. And how it works? It works in a way that a policeman stopping us. For example, we have our zero knowledge proof wallet on our mobile phone, and then he or she says us, let's verify you that you have just true or false the driving license. We issue the proof that yes, we have with this category for the simple car. Like as far as I remember, that's a B category. And when we send this proof to the policeman, he or she verifies it and says, yeah, yes, you have actually the driver license, move on, you can go. And in this architecture, there is no exchange of information between policemen and the government ID agency. If we issued this proof, it means that we are the only person who decides if we want to issue this proof or we do not want to issue this proof. Maybe we will say, no, we don't want to provide you any proof, and it will be our decision and our responsibility. Again, the same thing works for the smart contract because it's all algorithm, it's all mathematics. So if we exchange with the police officer the real ID, the real driving license, which is plastic one, here we can do it by sending certain numbers in a transaction. So this is how it works. So you see here that there's more privacy for you. You do not disclose information you do not want any other site to know about you. There is much more privacy for you in terms that and managing your own privacy information, that you're sure that there is no exchange of information between policemen and the government ID agency. They do not exchange data between each other. So you are the owner of your private data. That's the Web3. That's for what zero knowledge proof is standing for. One more important thing is that, strictly speaking, we do not need necessarily blockchain. So zero knowledge proof can work off-chain, a technology which does not require blockchain as a must. It can work solely by, so you can have your ID, you can issue this claim to the police officer. We do not see any blockchain connections, transactions here. But when we combine these two technologies, we get massive advantages. And the reason why we have it, I told you before, it's privacy and scalability. So again, wrapping it all up and having the general idea. So in a classical ID, we need classical trusted brick and mortar intermediaries like government. This is the zero knowledge proof. We can build it on blockchain, smart contracts protocol. For the ZK, it's open ecosystem. Anyone can interact with the smart contracts. For the IDs, we know that it's a closed system, centralized system secured by firewalls with very limited open parts. Why it's so closed, to understand, because we have this centralized database with all government licenses of specific country, and we know what happens if anyone can copy it. That's a lot of problem, but it's a matter of time when it will be copied. At global reach, we can provide privacy on blockchains for zero knowledge, and again, subject to massive data leakages with millions of IDs stolen. That's a classical ID. Each ID presentation, okay, we give full access to the data to verifier. Here in the zero knowledge proof, we reveal only the needed part, answering the question yes or no. And of course, we are the owner of the data. Only ID owner and verifier exchanging the data. In the classical ID, everything happens on another way. We do not control the data. We give lots of personal data, and then they start to, let's say, move somewhere, not depending on us. So Let's talk about development of the zero knowledge technology. So it started maybe 50 years ago, so it's quite fresh. Mathematicals, it has quite fresh mathematical background. And first zero knowledge proofs, non-interactive so-called, were presented in 1988. Before that, we had only the mathematical base for interactive proofs, which means that we need the whole session of exchanging of data between prover and verifier. It means that it's not possible to do in one transaction, but you needed, let's say, a number of transactions to prove that you have to prove a certain statement, meaning that if we take this example of the policeman and the driver, a policeman asks something for the driver is answering, then again question, then answer, question, answer, question, answer. And this interactive process with a certain probability gives the policeman idea that yes, you have your driver license. Now we can skip this interactive exchange of data and have so-called non-interactive proof. So only one proof. So you only send one piece of data, and based on this piece of data with the almost 100% probability, policeman understands that yes, you have your driver license. So that's it. Moving forward, so let's get more into the technology itself on so-called architectural basis of how it works. First, we have some private input and we have some public output, and we have some deterministic program. It's called circuit inside. I will give an example later. And what the prover is doing, private input, it means that that's the data which we do not want to disclose. So it's hidden data, and this stands for zero knowledge. So this data will not be known to the party you want to the verifier. You want to prove something. So, and we generate this zero knowledge proof. How? We have this function where as input we have this deterministic program, that's the mathematical algorithm circuit. We have this private input and we have public output. And what verifier is doing based on this data, the verifier only gets the public output and the zero knowledge proof. And connecting these two data with a special function, the verification stands for verification, we can get the verifier is getting the answer true or false for your statement. This is how it works. And the example is non-interactive zero knowledge example. Let's suppose we have the circuit. Of course, you have to understand that it's not possible to calculate private input from the public output, because it's a simple, if for example, it's a simple arithmetic function, 2 + 2 = 4. If we say, if our private input is 2 and 2 and public output is 4, then we do not need any proofs. We can actually calculate it back and understand that 2 and 2 can be used for actually getting the output. So the hash function exactly what we need, because as soon as you calculate the hash h from number, and how we generate proof, we actually take our circuit which calculated this hash, we take our R, which we as a prover know, and we also use the hash which we calculated. And when we send this proof to the verifier taking this proof and having the public output, having the hash, can answer to the question if we know or we don't know. These are the initial data from from the private input which we used. So that's how it works. This is an example of so-called Circom library, which we in our company Distributed Lab were using for actually working with the circuits and zero knowledge proof, which we used for identity management. So that's the function. So that's all in the libraries, and everyone can actually look at the Circom library and try to play with zero knowledge proofs. The Circom library, the whole getting even deeper into the technology, we know that Ethereum and Bitcoin, any blockchain is built on so-called elliptic curves. And of course, zero knowledge proof is also based on, not of course, but zero knowledge proof is based on also on elliptic curve. And the specific formula for this elliptic curve, you see it. It's called baby Jubjub elliptic curve. I don't know why they choose this name, but actually that's the name of this elliptic curve. And this elliptic curve is actually used with this specific finite field of elements. So you see how many actually private keys you can extract from this huge number. So v in power 2 equals u in power 3, then 168,688 multiplied by u power 2 plus u. That's simple formula, which you might actually familiar with this type of elliptic curves from your school, but they have this specific qualities which allow us to build blockchains on them, and even zero knowledge proof technology also using quite simple formulas. Now let's get closer to the technology which we use for IDs. It's called ZK-SNARKs. What stands for what in this ZK-SNARK word? ZK is zero knowledge proof, so we understand. Then succinct, it means that zero knowledge proof is smaller than the witness. Witness we call actually the private input data. That's something we do not want to disclose, and can be verified quickly. So it's exactly this quality which provides us scalability and allow us to use blockchains when we take lots of time and calculation power to calculate the proof, but as soon as we did it, it's very simple to check it, even on chain. We send the proof and the private output to our smart contract, for example, and that's enough for the smart contract to get this answer yes or no. Non-interactive, that's we already discussed. It doesn't mean that it means just we do not need to exchange a few times. We need just one zero knowledge proof, and that's enough for us to prove something. We do not need interaction and sending and receiving data with the verifier, between proof and the verifier. Argument means that we have the soundness of requirement. So cheating is extremely unlikely. So if you do not know the original number, it's not possible for you to prove it, which means that actually if we let's move to the example with this hash. If you do not know the number from which you calculated this hash, you will not be able to generate the proof. So that's the soundness. You cannot actually, by brute force, to choose the correct number. And knowledge stands for actually the secret information, the witness. We do not disclose it. It's not possible for a prover who doesn't have the witness to compute a valid zero knowledge proof. So that's what we just discussed. So that stands for ZK-SNARK technology. But ZK-SNARK is not without, let's say, vulnerabilities, and the key vulnerability is so-called trusted setup. What I'm talking about here is that before we start this exchange of parameters between prover and verifier, sending from the prover to verifier the proofs, we need to agree for the ZK-SNARK technology on a certain general so-called shared key. This shared key is generated as well. We have this today technology. It's called ceremony, which allows actually lots of parts. Maybe you have 10 or 20 people combining together to generate this trusted setup, meaning that as soon as only all of this 20 will keep the secret, again actually connect to each other, then they can actually have these keys, and having these keys of the trusted setup will let you to fake the proof. So that's the key problem. But as soon as all the parties which were in this ceremony, or one even of those who take part in the ceremony, destroy his or her part of the key, then it's not possible to generate the data which will allow to make fake proofs. But again, you need this shared key only to generate it only one time, that's trusted setup, before you start exchanging the data. So it may be in reality, we have 15 people and on different parts of the world, they get all their part of the key, they get together in an electronic way, they generate this shared key, then destroy their parts of the key, and everyone in this starts to using this trusted setup. I mean, the provers and the verifiers on this specific zero knowledge proof implementation. That's it. If you ask me a question, if we have the next level of technology which will not, which does not require the trusted setup, yes, this technology is called ZK-SNARKs, not SNARKs, but SNARKs. It's already available, and it allows work and exchange between the prover and the verifier, the data without initial trusted setup. But the drawback of this technology that it's much more complicated. It takes much more time and resources to calculate the proofs, and a little bit more efforts to verify these proofs. So it's more calculation hungry, computationally hungry technology. Now let's go to the specific zero knowledge proof use cases. Actually, we will talk about the free identity management. We'll talk today, and the zero knowledge rollups and private accounting systems we will talk on the next lecture. So let's go with identity management. I will talk about identity management based on the Polygon ID system which they built and which we also used for our let's say work with the zero knowledge proof technology. So first I address you to this digital identity for everyone. This is Tony Blair with William Hague saying that everyone in Great Britain should be given a digital ID incorporating passport, driving license, tax record, qualifications, Sir Tony Blair and Lord Hague, Richmond, what they say. We all understand that if everything about everyone will be in one centralized database, that's the only way, matter of time when this database will be stolen, with a huge impact on the whole system. If some criminals will know your ID, your driving license, tax records, qualifications, right to work, I don't know anything about you, everything about you. That's not good. And of course, if we want to build this type of huge big brother systems, the best way to build it is to build it in a decentralized way using zero knowledge technology. When you are, as a citizen, Great Britain or any other country, the owner of the data, your private data. You have the claim, the ID, which is issued by the government to you. And when some entity, policeman, or I don't know, tax administration is applying to you, you issue for them proofs and only give them the data they need, answering to their questions, yes or no, true or false. So that's much better system. And this system actually, it's much more difficult to stall the database because it's distributed between everyone. So if you lost your keys, that's only your problem. You can restore it. We need a special procedures for this, but it's all possible to manage. It's much better technology for the futures, the case, than the classical one. In general terms, talking about digital identity, we mean that one person can define and have many identities, meaning that you can be part of the club. I don't know, you can have a pass to your gym and all these identities. Anything can be an identity. That's also clear. So we can prove anything. Answering the question yes or no. Do you have a right to get into the gym? We can generate the proof. Yes, we can. We only verify this, yes or no. We do not actually need to tell the other side, the verifier, what's our name, what's our age, and all the rest data. They do not need actually. In Ethereum, the identity is an externally owned account. That's the account which maybe all of us, or I think you all use, or a smart contract. Smart contract is also can be an identity. The claims is actually the ID. Any active identity can do any claim. Okay, so it means that if we are friends between each other, I can issue for you the claim that you are my friend, and you can issue for me. You will be the issuer, I will be the issuer, you will be the prover, and I can be and I can request from you the claim that I'm your friend. You issue me this claim, and then we can prove to the third person that I am your friend, and you can prove to the third person that you are my friend, issuing the proof. So that's how it works. Claims create a relationship between identities. That's what I was just talking about the example of friendship. And claims can be public or private. The proofs on-chain and off-chain blockchain is not always required. So that's what I was talking about. And this friendship story, actually, we do not need blockchain. We have 3 persons, 2 of them friends, each identity, each friend, 2 of these friends issued for each other the claim, and basing on this claim, both of them issued the proof to the third person that they are the friends. And of course, we can issue so-called non-reusable proof. Non-reusable proof. So I will talk about it later, but let's focus on the Iden3 standard. So that's very important. The standard which Polygon technology is using, called Iden3. Iden3 is built on the Circom libraries. So it's privacy by default and by design, self-sovereignty of identity. So there is no central party that controls all the identities. So that's great. It means that no one can switch off all identities. That's not how it works. So it's a centralized system. The identities are controlled by whoever is determined at creation time. So if I created the identity, so I control it. If I created a claim for you, you are my friend, I control it. At any time, I can revoke it. That's only my decision. Key management, accessibility, scalability, meaning that anybody is enabled to create unlimited entities. Okay, any identity can create as many claims as they want. So if I have 1,000 friends, I can issue these claims that they are my friends to everyone. So I issued 1,000 claims. Interoperability, of course, based on the standard. But where we need the blockchain, we need blockchain if we have so-called, if we actually want to manage our claims. Direct claims. Claims are stored in the Merkle tree and the Merkle root stored on chain. You do not need to get into this Merkle tree story. I can only say that why we need this blockchain, this Merkle tree and this Merkle root, which is stored on chain. First of all, if we have, for example, let's say the government of Great Britain, which issues every day, maybe thousands, maybe tens of thousands of IDs. And how any verifier can prove that you have this ID, because of course the government is issuing IDs and revoking, meaning that maybe the term of use is missed, maybe for another reason we revoke this your ID, and we can and the government can use for this the blockchain, maybe Ethereum blockchain. When we add, let's say 10,000 IDs for the day, then we pack these IDs into Merkle tree, and we have this root of Merkle tree. That's just one number, and we send one very cheap transaction to the Ethereum blockchain as a government. And everyone around us can understand from this root that we added this 10,000 IDs, maybe million IDs, maybe 10 million IDs, maybe 1 billion IDs, doesn't matter. So this is the way for scalability. And when the person who received claim from our government wants to prove something that they have ID to any verifier, the verifier gets the data as a proof that the prover has this ID, and to check if this ID was not revoked, the verifier, maybe smart contract, gets to this Merkle tree root and checks with this root if your ID is still valid. So this is how it works. Maybe too complicated for you to understand, but just get the general idea. So we need this on-chain data, this Merkle tree technology and Merkle root to store millions and billions of data. Because we cannot send every ID transaction to the blockchain. That's not scalable. That's painful. And getting back to non-reusable proofs, if you will want, you can separately go and read deeply about it, but just believe me that it's possible to generate the proof, which can only be accepted by a specific address. So which means that we as a prover generate the proof, and this proof can be actually used, meaning and have an answer to the question yes or no, only this address. And if this proof goes to another address, this address will not get this data. So that's also, I will not get deeply into this technology, but just read it into the presentation or read it separately. And the specific, very concrete example of zero knowledge proof vaulting implementation, we have the issuer, which has some KYC procedure and onboarding new participants. Let's say it's some DAO. Then we have a voter, that's the voting system. And this voter applies, or user or approver applies to our issuer and asks for identification. Issuer sends so-called ZK claim and confirms that, yes, we are member of the DAO and we have right to vote for some DAO decisions. DAO is decentralized autonomous organization, if someone doesn't know what it is. Then we have some voting organizer, that's DAO. Members decide on a specific question. And actually, they put this data on chain, and we have so-called voting contract that's on chain. And if our voter wants to vote for a specific question, then he or she sends the transaction with ZK proof that this address is a DAO member, and actually the decision, we accept this, we vote yes for this decision or no. What later actually our voting smart contract is doing, it checks our proof, and if we are a DAO member, it accepts our vote. So everything is clear, meaning that if we are not DAO member, we will not be able to vote. We cannot vote next time because smart contract remembers our ID, and everything is clear and transparent. So this is a very concrete example which we in distributed lab realized on EVM blockchain. So what else we can do with our identities? Of course, that's access control, physical or logical. I'm going to buy an alcohol, so I issue proof if I have 21 years old. That's a single sign-on. Decentralized applications, if you want to log into a certain site, website, without revealing your personal details, you can use ZK proof to log in, and the website will not know who you are. The only thing website will know that you have access to this website. Internet of Things, centralized applications, signing documents and private messaging, voting census, voting example we already discussed, token transfers for KYC identities, that's also what we discussed. I gave you an example when you want to supply assets on chain to a certain pool, and how you do it, you just you issue ZK proof that you have a KYC from maybe some trusted centralized exchange or government or any other issuer. So that's it for today. Next time we will talk about ZK EVM, zero knowledge Ethereum virtual machines, and private blockchains, an example of Zcash. That's it. Thank you for your attention. If you have questions, please, ready to answer.
Thank you very much, Serhiy. If that's end, I stopped our recording.